Good morning, students. Welcome to Complex Analysis Live Lectures. In this class, we'll discuss some examples of um, Maclaurin series, Taylor series, and Lorentz series. Then we'll discuss the absolute and uniform convergence of Fourier series. Okay? So let's start with some examples. So first one, so we'll see some examples of Taylor. In particular, if z naught is equal to 0, it is Maclaurin. Okay, Taylor or Laurent series. Okay, then we'll move to absolute and uniform convergence. So start with first example. So consider f of z is equal to e power z. We know that it is analytic everywhere in the entire complex plane. Okay, so whichever disk you take, it is not a problem. It should have this power series representation. So we'll find what is its Maclaurin series. Okay, we know that how we can write Maclaurin series. So Maclaurin series for this f of z, which is e power z, is equal to summation f nth derivative evaluated at 0 by n factorial, okay, upon z power n. N is from 0 to infinity, right? But here our f of z is e power z, so f of z is e power z. So this implies any nth derivative, we already know it is same as any nth derivative is again e power z. This implies evaluated at 0 is e power 0, which is 1, right? So therefore Maclaurin series of e power z is, we can write this as, this will become 1. So z power n by n factorial, which we already know, at least in calculus, that e power x is summation x power n by n factorial. Okay, this we can use this to find several examples. Say for example, if we want to find Maclaurin series, or we can say even Taylor series also, because at z is equal to 0, for the function say f of z is equal to z square into e power 3z, then it is easy, we can find the, because e power z we have here, so e power 3z is this, wherever z is there, so that is this 3z whole power n by n factorial. This is for e power 3z, right? Then this implies z square times e power 3z is, you can take multiply z square inside, so n is from 0 to infinity, 3 power n z power n, then you have z square here, right? By n factorial we have z square here, right? So if you take that inside, then it is summation 3 power n by n factorial into z power n plus 2. Okay, this is the Maclaurin series. Or if you want to, they can, this is, you can, we can stop here, or we can rearrange this one. We can rearrange this as this, we can write as instead of z power n, we can write here n, then n starts from 2 here, then this will become n plus 2. Okay, because 0 factorial 1 and so on. So if I write from, instead of 2 0, if I write from 2, then this is 3 power n by n factorial. Okay, uh, this sorry, is not n factorial, this this will become z power n, and this will become n minus 2 factorial. Okay, and this become 3 power n minus 2, so that I can write here 3 power n minus 2, so I can write here 3 square like this. Okay. Okay, now let's take another example. Say suppose, find, take f of z is equal to sin z. Okay, we can find Maclaurin series in two ways. One is, because it is differentiation is either cos z or sin z. Okay, then when at 0, when you substitute at 0, that value will be either 1, -1 or 0, depending on what n it is. Okay, then we substitute there. Or we know this one, sin z, we can write this as e power iz minus e power minus iz upon 2i. Okay, then substitute the value of this e power iz, okay, wherever z is there, iz, then simplify, and this implies this is same as 1 by 2i summation e power iz, that means iz whole power n by n factorial minus summation e minus iz whole power n by n factorial. Okay, n is from 0 to infinity. And because here you can take this sum inside also, it is possible here. Then we can observe here this, I can write this as 1 by 2 power I into summation this I power n, okay, then z power n, I power minus 1 whole power n, z power n. So here you will have 1 minus 1 whole power n by n factorial into z power n. Okay, n is equal to 0 to infinity, right? Fine. Then now if n is odd, then this will become, if n is even, then this will become plus 1. So 1 minus 1, 0. So when n is even, these terms won't exist here. So when is odd, then this will become minus 1, minus of minus 1, plus 1. So 2 and 2 will get cancelled. Okay, so I will here I power n is there. I have not written here I power n. Okay, now if n is odd, say for example I cube, then I cube is I square into I, but I square we know it is minus 1. Okay, and I'm sorry. So before we will write here 1 minus 1 whole power n is equal to 0 when n is even. Okay, so therefore we can replace this summation wherever n is even, we can leave out, and we can only write that as odd. So how we can write that is 1 by 2 power I summation n is from 0 to infinity. So it is of the form 2n, if it is that it will be out. So it is 1 minus 1 whole power 2n plus 1 upon, okay, 1 n factorial z power 2n plus 1 and I power 2n plus 1. Okay, and here this 1 minus 1 whole power 2n plus 1, because this is always odd, whatever n it is, this is minus 1, so this will be 2. So here this value, and this I power 2n plus 1, we can write this as I square then whole power n into I, but I square value is minus 1. Okay, so this value is minus 1 whole power n into I. So therefore if you put all those things, then sin z is equal to 1 by 2i summation n is from 0 to infinity, this value is 2, and z power 2n plus 1 and minus 1 whole power n and this I. So I can write that I here divided by n factorial. Okay, so this 2i will get cancelled. So what is remaining here is n is equal to 0 to infinity, okay, minus 1 whole power n z power 2n plus 1 by n factorial. Okay, this is the Maclaurin series for sin z. Okay, fine. Now we also look at one more interesting example which is used to solve many examples. Say let's find another one, fourth one. So let f of z is equal to 1 upon 1 minus z. Okay, then how we can find this one, this we want to find the series, Maclaurin series for this. So we can show that this value is actually summation z power n. How we can do that? Yeah, here this function is not analytic at z is equal to 1, because z is equal to 1 is a singular point, right? So we will consider the region mod z less than 1, then this function is analytic, okay, in this region, right? So therefore we have f dash of z, okay, f dash of z which is equal to 1 by 1 minus z whole square. Okay, then f double dash of z, you can check that this is 2 by 1 minus z whole cube, okay, then and so on. Of course, next time it is f triple dash of z is 2 into 3, which is 3 factorial by 1 minus z whole power 4, and so on. So therefore f nth derivative of z is n factorial by 1 minus z whole power n plus 1, right? So in particular when it is evaluated at 0, that means fn of 0 is this n factorial, that's all, by 1. If you want to write 1 minus 0, which is 1, okay, that is n factorial. Therefore what is Maclaurin series? So Maclaurin series for this f of z, which is 1 by 1 minus z, is summation f n of 0 upon n factorial by z power n, right? N is from 0 to infinity, but here fn of 0 is n factorial, and n factorial will get cancelled. So what we have here is this. So therefore 1 by 1 minus z is summation z power n from n is from 0 to infinity. Okay, we'll use this several times to simplify Taylor or Maclaurin series expansion. Okay, now let's move to some series. Take an example. So find, okay, Taylor or this Maclaurin series for f of z, okay, minus 1 upon z minus 1 into z minus 2 for the following domains. The domain mod z less than 1, okay, then 1 less than mod z less than 2, and another one is mod z bigger than 2, but of course finite. Okay. Now how we will do this is how we can simplify this f of z, and we'll see whether it is analytic. If it is analytic, then we get the Taylor, or if in Lorentz series we get when we have annular region. Okay. Fine. Let's find the solution. So our f of z is given that minus 1 upon z minus 1 into z minus 2, right? This, by using partial fraction, we know already we can write this as 1 by z minus 1 minus 1 by z minus 2, because z minus 2 then minus z plus 1, okay, so minus 1 you will get, right? This is our f of z. Okay, now if we consider this first one, so first case is the domain is mod z less than 1. So when mod z is less than 1, here when mod z is less than 1, this f of z is equal to 1 by 1 minus z, which already has this expansion which is z power n. So obviously here I can take this f of z, we can write it as minus 1 by 1 minus z. Okay, so I have taken minus common here. Then similarly, this we have to write in such a way that whether it fits in this domain or not. Okay, so in place of z we will take z by 2 like that. So here we will take minus 2, okay, common, so it will become plus half, then it is 1 minus, okay, 1 minus z by 2. Okay, the 2, if I, this will become 2 minus z, here it was z minus 2, so we have taken minus, that's why it become plus, right? That is the only thing we did. Now we can observe that this whatever inside here, because mod z is less than 1, then mod z by 2 is less than 1 by 2, which is less than 1, right? So since this mod z is less than 1 and also mod z by 2 is less than 1, okay, by example whatever we have just seen, we get this 1 by 1 minus z, this is equal to summation z power n, okay, and 1 by 1 minus z that our z is z by 2. Okay, this is what you will get is z by 2 whole power n. That's right. So therefore, if we substitute these two values there, what we will get? Therefore, our f of z has a expansion some minus summation z power n is equal to 0 to infinity because minus is there, and then we have plus half into summation z power n by 2 power n. Right, either you can leave it here or we can further simplify into one more step, which we can write as summation this is 1 by 2 power n minus 1, 1 by 2 power n plus 1, sorry. Okay, and then this is minus 1. This is the coefficients z power n is from 0 to infinity. Right, this is the Taylor series of our function f of z where mod z is less than 1. Okay, fine. Now consider our second domain, which is 1 less than mod z less than 2. Okay, every time idea is we will see something like mod z, that z, some z prime you say mod z prime is less than 1. If you can make it that, then 1 minus whatever you have here, that z prime, that value we know it is, what is this one? Summation z prime for n. Okay, so here again our f of z is what? This 1 by this minus 1 by 1 minus z. Here f of z is 1 by z minus 1, 1 by z minus 1 minus 1 by z minus 2. This is our f of z. Now how we can write here? This implies our mod z, that means our mod z is greater than 1 and also our mod z is less than 2. So this is no problem, I can bring it here. This that means this is same as mod z by 2, okay, is less than 1. So wherever if I have something like z by 2, that 1 minus z by 2, then I can apply that result, right? Now what about here? Here it is not mod z minus 1, so this I can simplify same as 1 by z. This will become less than 1. Okay, that means here the first one that we want to change in place of z we should have 1 by z form, right? So how we can do that? Here we will take, so 1 minus, so first of all this you write as minus 1 by 1 minus z. Okay, no need to write minus common. So if I take z common, z in this one, if I take z common, then it is 1 minus 1 by z. Okay, and here what we will do, we will take out minus 2 common. So that means that expression what we did in first a, we don't need to change anything here. This you simply write as 1 minus z by 2. Okay, so this whatever we did here, this is will be as it is work here because mod z by 2 is less than 1, right? Now this is same as 1 by z times, this is 1 by 1 minus 1 by z. We know mod 1 by z is less than 1. Okay, so therefore this is what? Summation 1 by z whole power n by the previous example. Okay, and then plus 1 by 2 times summation, now this is 1 by 1 minus z, so where our z means z by 2 which is less than 1, so this is same as z by 2 whole power n, right? So whatever we can simplify further, we can simplify this summation n is equal to 0 to infinity, this 1 by z power n plus 1 we will have, okay, plus summation n is equal to 0 to infinity z power n by 2 power n plus 1. Remember this is z and this is 2, so don't confuse. Okay, so this involves both positive powers as well as negative powers of z, right? So it is a Lorentz series, right? And that we can see because it is, we are having a domain which is annular domain, right? Now let's see third one. So third one is 2 is less than mod z is less than, fine. Okay, now in this case how we have to do it? Here again this, because mod z is bigger than 2, so 1 by mod z is less than 1 by 2. Okay, so this bring it here and you bring it here. So first one as well as second one, both here we have to make it 1 by z. In both places we want to change. So therefore our f of z, we want to write this as 1 by so this one we will take it as it is, 1 by z into, so 1 by z into 1 by 1 minus z. Okay, now the second one also we want to change. Okay, second one also we want to change, right? So that it will be 1 by z term. So 1 by z, how you can take here, minus 2. If I take common z, if I take common here from this z, then it is 1 minus 2 by z. Which one we want? 1 by z we want, right? That is fine. 2 by z, 2 by z will be less than 1. Okay, and this 2 by z is less than 1, right? So here if we simply take from this z outside, so minus will be there. So minus z, if I take, then what we have here, 1 minus 2 by z. Okay, so 1 minus 2 by z. So 1 by z also is less than 1 and 2 by z is also less than 1. So we can have power series, Maclaurin series for this, which is summation 1 by z whole power n is equal to 0 to infinity, right? And then minus 1 by z summation, this is 2 by z whole power n is equal to 0 to infinity, right? So what we have here is summation 1 by z power n plus 1, n is equal to 0 to infinity, and this also if we simplify, 2 power n by z power n plus 1. Okay, so if you see this, both have same denominator, so this is same as 1 minus 2 power n by z power n plus 1, n is equal to 0 to infinity, right? So that means here we can see that when n is 0, then this is 1 minus 1, which is 0. So you can start even from 1 also, there is no problem, because n is 0, then is 2 power 0 is 1, 1 minus 1 is 0. So you can even start from this, we can start from 1. So no need of starting from 0. So when then you can see that it has all negative powers of z. Okay, so this is Lorentz series where no positive powers are exist here. This is the f of z expansion when mod z greater than 2. Okay, fine. So these are all some examples. Let me share some exercise problems for your practice. If you have any difficulty, you can please ask me. Okay. Yeah, so these are some of the exercise problems. Find the Lorentz series of this function f of z equal to z square sine 1 by z square. Okay, we already know sine z. So for that sine z, wherever z is there, 1 by z square you substitute, then multiply by z square and simplify, you will get this one. Okay. Similarly, find the Lorentz series for e power z by z plus 1 whole square. See, we know already e power z. Okay, so as I said, you write e power, in place of z you take z plus 1. Then write the e power z plus 1 expansion Maclaurin series, then simplify, because z plus 1 whole square is there, right? This is same as one way you will get, it is same as e power z by e. Okay, so but on the other hand, e power z, this is nothing but summation z plus 1 whole power n by n factorial, right? So from this e power z is nothing but sorry, this one is not by e, it is e times this. So therefore e power z is nothing but 1 by e into this one, right? Then you further simplify, and these two terms, because z plus 1 whole square is there, so it will cancel, and what is remaining is this one. And similarly solve other problems. If you have any difficulty, you can please ask me. Okay, see, until unless you solve, however you feel like you understood, until unless you start solving the problems, you never try to see where you will get the problem. Okay, understand the domain, how we can split that, how we can write that in standard form, and so on, right? Fine, now let's move to another section, which is absolute and uniform convergence of power series. Okay. So it is about absolute convergence. So let me write the theorem which says that suppose if a power series, the summation an z minus z naught whole power n is from 0 to infinity. Okay, suppose if it converges at a point, say suppose when z is equal to z1, okay, where z1 is different from z0. Okay, that means if this power series converges at least one point different from z0, okay, then this power series is absolutely convergent. Then it is absolutely convergent at all points, at all points z in the disk mod z minus z naught less than r1, where r1 is nothing but where or r1 is distance between z1 and z0. First again try to understand theorem. What it says is that if a power series, given power series converges at a point say z1, then it converges absolutely at all points in that disk, okay, whose radius is z1 minus, whose radius, okay, is nothing but the distance between z1 and z0, right? That means let's try to understand this through picture, then we can prove it is not a problem. So let me draw some shape here. Okay, we have this. Then now we have say suppose z0 is here and z0, this is z0, and suppose at z1, this is our z1. Okay, this converges, this power series converges, this is different from z0. Then what we are saying here is that this series is absolutely convergent at all points z in the disk mod z minus z0 less than r1, where r1 is, so this much is our r1, this is our r1. Now if you take the disk, so let me write here. So if you take any point z inside this, anywhere you take, at all those points, this series is absolutely convergent. Okay, that is the meaning of this statement. Fine. Now let's prove this one. To prove, so let z is a point in this disk. Okay, and then we want to prove that it is absolutely convergent. That means, so our claim is, so let z be any point, sorry, be any point in the disk mod z minus z naught is less than r1, where our r1 is mod z naught minus z. Okay, so because this is strictly less than this implies mod z minus z naught upon mod z naught minus z1 is strictly less than 1. Okay, so if you want, you can call it this this value as rho. Okay, and what we know that this rho is less than 1, right? And our claim is to show that, what is our claim at this point z, we want to show that mod summation, because absolute convergent we want to show, summation mod an into z minus this z naught whole power n, this series converges so that it will become absolute convergence, right? This modulus should converge. Now, if we want to find this, how we can simplify? We will try to get this idea. So, an modulus of an into z minus z naught n. This obviously we can bring numerator denominator this factor. So, this an into I'll multiply z naught minus z by z naught minus z1. Okay. Then uh, here what we have already here is z minus z naught whole power n. So multiply this. We have same. These two are same, right? Then this we can rewrite this as mod n into this z minus z naught. Okay, z minus z naught by z naught z1 minus z0 whole power n, and what is remaining here is z naught minus z1 whole power n, right? This we can write this as mod an into z naught minus z1 whole power n into this is nothing but z minus z naught by z1 minus z0, that is our row, right? So this is, you can write it as rho power n. I can simply this I can write it as rho, sorry, rho power. Now, what can you say about this one? Mod an z naught minus z1 whole power n. If whether it has some, can it be some finite value or bounded something for any n? That is because since so now since this summation an into z minus z naught whole power n, this power series converges at z1. That means the sequence of partial sums converges. So we know when sequence converges, then that sequence is bounded. So all the terms in that sequence, they are bounded by a given positive number. Okay. So there exists, you can call it m greater than 0, such that modulus of an into z minus z naught whole power n is less than or equal to m. This is true for every n. Because the series converges means its sequence of partial sums, okay, converges. Okay, that means that if you call it this an, whatever we are calling, that tends to 0, right? Then if the sequence converges, then we can have a bounded, right? That terms are bounded. Okay, so therefore we can have this, there exists some m such that mod an into z minus z naught whole power n is less than or equal to m, right? So therefore, what can you say about this one? Therefore, mod an into z minus z naught. Oh, sorry. Here this converges. So therefore, it when you substitute after z1, after z1, after z1, when you substitute that, then this is less than or equal to m. So therefore, mod an into z minus z naught whole power n. This value is, which we have simplified, is equal to this, but this is less than or equal to m. So therefore, this is less than or equal to m times rho power n, and this is true for all n, right? Then mod an to z n is from 0 to infinity is less than or equal to m into summation rho n. Okay. Now this rho is less than 1. Okay, which is a real number. So we have a real sequence series. Okay, geometric series. So we know this is a geometric series, so which converges and tends to 0, right? So yeah, so this since the geometric series summation rho n is from 1, n is even from 0, you can take it 0 infinity converges for rho less than 1, and by using comparison test, the left hand series whatever we are having, that also left hand side series also converges, right? So summation mod a n z minus z naught whole power n. What we have here is therefore summation a n z minus z naught whole power n converges absolutely. Okay, for all z, okay, in mod z minus z naught, right? This is about absolute convergence. So what we can understand here, the proof is not a difficult one, but this statement has a lot of meaning. So what it says here is, we can have a remark. The theorem that the theorem says that there exists a circle, okay, inside that circle it converges everywhere absolutely. The theorem states that if series converges at a point, at even one point, okay, other than z naught, okay, then it converges absolutely everywhere in some circle, okay, centered at z naught. This different from z naught, okay. That is very interesting. And so we can, once there is at least one circle, then we can have a the largest circle where it converges is called circle of convergence. The largest circle which this is convergence is called circle of convergence. Circle of convergence. And that means if you take any point outside this circle of convergence, then at those points it is divergent. That means the series diverges at all points outside the circle of convergence. And later we'll see it is called radius of convergence. The radius of convergence of power series is nothing but this circle of convergence, radius of the circle of convergence. Okay, that we'll see later. Fine. Now we'll move to what is meant by uniform convergence of. So to move to uniform convergence, we'll have some terminologies. What is meant by uniform convergence of the series? Okay. Okay. So what is meant by uniform convergence? For that, say let this summation, the series summation a n z minus z naught whole power n has this circle of convergence. That means this is the largest circle, mod z minus z naught equal to r, where this this power series is convergent. Okay. Fine. Now we'll denote, say suppose s of z, z is any point here. Okay, for z any point in this inside this circle of convergence. So if we want, we can write that before. Let z be any point in inside the circle. This mod z minus z naught is equal to r. Okay. Then for this z, you take s of z, which is equal to, you denote this by summation an, the value at z minus z naught whole power n, and this partial sum Sn of z is summation, this is n is equal to 0 to infinity, and this is from a n z minus z naught whole power n, this is up, n is from 0 to n minus 1, sum of first n term. Okay, this of course in this mod z minus z naught less than r, right? This is for all z belongs to mod z minus z naught strictly less than r, that means point inside this, which I already mentioned here, right? Okay, now they let rho n of this z, which is s of z minus Sn of z, okay, be the remainder function we know, right? Then this by result absolute convergence, what we have proved is that this summation a n z minus z power whole power n, this converges everywhere inside this circle. So in particular it converges at this point z, right? That means this s of z converges. Okay, s of z converges, that means this rho n of z, okay, tends to 0. So since this s of z converges, okay, what we will get here is this Sn of z, okay, minus this s of z, or s of z minus Sn of z, whatever you take, this this tends to s of z, okay, as n tending to infinity, right? Therefore this rho n of z tends to 0 as n tending to infinity. Now what is meant by saying that this function tends to 0? That means given epsilon greater than 0, there exists say some n epsilon, okay, such that modulus of this rho n of z is less than epsilon for all n greater than or equal to, this n epsilon, right? Now if this uh, given any epsilon, if we can find this n epsilon, okay, which depends only on of course this epsilon but not on any z, if this is true, that means we say that if n epsilon does not depends on z, then we say that the series converges uniformly. Okay, so what is the meaning of that? That is, given epsilon greater than 0, there exists this n epsilon such that for all z, okay, for all z in that disk, inside the circle, what we should have is this modulus of rho n of z is less than epsilon. Of course this is true for all n greater than or equal to n epsilon, or that is same as saying that modulus of s of z minus Sn of z is less than epsilon for all n greater than or equal to, this is capital N epsilon. Okay, so if this scalar whatever we are finding that does not depend on z, then we say it is uniform convergence. Okay, fine. Now let's prove this result, which says that if we have a, a z1, if z1 is a point inside the circle of convergence, mod z minus z naught is equal to r of the power series summation an into z minus z naught whole power n, then this power series converges uniformly, then this series converges uniformly, okay, in the closed disk, in the closed disk, mod z minus z naught less than or equal to r1, where of course what is r1? R1 is distance between z1 and z0. Okay, z1 minus z0. Fine. Let's again understand through the picture. What it says is that if we have a circle of convergence and if we have z1, okay, z1 is any point, then we know by previous theorem that um, it converges everywhere inside that. Now what we are saying that it converges everywhere inside that disk mod z minus z naught is less than or equal to r1. So you change z1, you will get another disk. Okay. So let's draw this picture, then we will prove this. So again, what we have here is prove this. So we want to prove that if you take any z, okay, inside this disk, mod z minus z naught is less than r1. So what is r1, and that we will write first. Okay. So suppose we have here, okay, then we have, first we will write the r, which is circle of convergence. So we will have it a little bigger one. Suppose say this is our z naught. Okay, this is our z naught, and assume that we have this circle of convergence. That means this is the largest circle possible where is convergent inside this circle. Okay. Fine. Now z1 is any point. So this much is our, so whatever we are calling here, this much is our r, this distance. Okay. Now take a point z1. Take a point z1. Say suppose this is our point z1. This is our point z1. Then we are saying that if you take the, we want to show that this series converges uniformly in the closed disk mod z minus z naught less than or equal to r1. So this much is our r1. Okay, and closed disk, that means I will take even points on that also. Okay, assume that this is circle. Okay, so you take any point z here. If you take any point z inside this, then we want to show that in any z, because uniform convergence means not locally. Okay, at all these points it converges uniformly. That means given any epsilon, we can find a n which does not depend on any z, right? That is what we want to show. Now how we'll prove is that, because now the idea is we would like to show that the series is absolutely convergent at this point z1. Why? That is because this is the, whatever we are having this circle, that is the circle of convergence. So if I take a point anywhere here or anywhere here, anywhere you take, okay, at that point also it is, so you can call it suppose z prime. Then at z prime it is converges, right? So it converges at z prime. Therefore if I take any disk, okay, centered at z naught, any disk, if I take like this, so assume that this is the disk, huh? This is my z naught. So this is my point z prime, and this is z naught. Okay, then at inside this, everywhere it is absolutely convergent. So in particular, z1 is inside this one, so therefore it is absolutely convergent at z1, right? So what we can write here proof, since the series series summation an z minus z naught whole power n is convergent at all points inside the circle of convergence okay, which is far away from z naught compared with z1. Okay, so there are points inside the circle, okay, which are far from z naught, okay, than z1. That means the distance from z0 to z1 is the distance from z0 to z prime. Z0 to z prime distance is more and z0 to z1 is less. Okay. So now this, say we have just taken z prime for example. Okay. Then if we by the absolute convergence theorem, what we know is that if you take the circle from centered at z0 and radius z0 to z0 z prime, then everywhere inside it is absolutely convergent, right? Therefore the series summation an z minus z0 whole power n is absolutely convergent, right, at every point inside this. So in particular it is absolutely convergent at z1, right? So therefore the summation an z minus z0 whole power n is absolutely convergent at z1 in prime. Okay, that means that is same as saying that summation mod an z1 minus z0 whole power n, this converges. Okay, this series converges. Fine. So we will denote, we will have some notation. So let the rho n of z, which is, we know this is remainder function, which is limit summation n is equal to n to m an z minus z naught whole power n as m tending to infinity. See what is we when we discuss the some notations here. Let me, yeah. Here, if you see for any series, rho n of z is s of z minus sn of z. That means if you take this difference, what we'll get is it starts from n, capital N terms onwards. Reminder, right? Capital N term onwards. That n to infinity, we can write it as, instead of writing n to infinity, you write n to m, then vary m tending to infinity. Okay, this one. And other one, which is sigma n, that is for this one, which is limit sigma mod an z1 minus z0 whole power n. Okay, n is from n to m and m tending to infinity. Okay, so we have taken this reminder functions for this series and for this series. Okay, we know this sigma n converges. Sigma, this converges, that means sigma n tends to 0 because this is the remainder one, this tends to 0. So we can use this one, this tends to 0 as n tending to, then sigma n tends to 0 as n tending to infinity. Okay, fine. Now we'll see what can you say about this modulus of, that means whether it converges or not. Because our idea is we want to show that this rho n of z is less than epsilon. Okay, it doesn't depend on z, right? So what is modulus of rho n of z? Modulus of rho n of z is, you can take modulus inside limit, because modulus of summation n to m an z minus z naught whole power n. Okay, then this is, now the modulus if you take inside, it will become less than or equal to mod an mod z minus z naught whole power n. N is from n to m, small m. Fine. Now z minus z naught And what is relation between z minus z naught and relation between z minus z naught? So this is z minus z naught, and the other one is z naught minus z1. Okay, so this one is inside this one, so therefore this is always less than or equal to z naught minus z1. Okay, so we can use the fact that since mod z minus z naught is always less than or equal to mod z1 minus z naught, so what we have here is this rho n of z, we get mod rho n of z is less than or equal to limit m tending to infinity summation n to m n this z minus z naught now I can replace by z1 minus z naught whole power n. This is precisely, this is whatever we are having here, right hand side is precisely sigma n. Okay, so therefore this is nothing but our sigma n, implies rho n of z is less than or equal to sigma n, right? Now we know as sigma n tends to 0, as sigma n tends to 0 as n to infinity, so epsilon greater than 0 is n epsilon. Sigma n mod is less than epsilon. So for all n greater than or equal to n, this one, right? Therefore modulus of rho n of z is less than or equal to sigma n, which is less than this, okay, is also less than epsilon for all n greater than or equal to n epsilon, which we can see that this is not depending on z. Whatever z we started with z anywhere in this disk, we got that is less than epsilon, right? So therefore this rho n of z is less than epsilon. That shows that this rho n of z is the remainder function of this power series. So this series converges uniformly. Therefore summation an z minus z naught whole power n converges uniformly, okay, in the disk mod z minus z naught is less than or equal to r1, where r1 is the distance between z1 and z0. Okay. So remember, you started with some z1 inside this. Now I can change this z1 anywhere, I can get this. Okay, so what we can understand here is that we can have whatever circle we take inside this circle of convergence, okay, and that circle and everywhere inside, it is uniformly convergent. Okay, fine. We'll stop here and we'll see some other properties of analytic functions next class.